Hello everyone. Let's talk some more. Last time that we were together, we talked about the Serway book, topic 18, in other words, chapter 18. Let's talk about chapter 19 for a bit. We'll see what we can do. We'll talk a bit about chapter 19, and over the course of some time, we'll finish chapter 19, these problems that I want to do. We are going to be doing more practice physics from the Serway books, the Serway and Buell book, 11th edition, often called the Serway book, as you know. It's going to be topic 19 that we're going to talk about. Now, topic 19, I call chapter 19. Chapter is kind of the colloquial way of calling any chapter. You call it a chapter, I guess, but they call them topics or chapters. For us, when we say that, they're synonymous. So for topic 19, I call chapter 19. For topic 19, it'll be these 8 problems. Topic 19 problems 9, 37, 39, 55, 58, 59, 60, 74. So those 8 problems, we'll get those done. I'd like to hook back just a little bit, somewhat briefly, to topic 18, really quickly, problem number 47. The answer that we gave there, that A was at higher potential, than B, is the right answer. I believe it to be the right answer. It's the right answer. It's our assumption it's the right answer. We believe the notes that they gave us and the answer key and discussion about what's going on here, I think they have it right. So I'm not really going to debate that. I'm going to concede that it's correct, but for that to be the case, now remember the way we had done the problem is this blue line right here was simply not present, and then we drew conclusions with the blue line simply not being present. The conclusions drawn were fine. They're correct. I believe a little more intuitive way to look at this is put a wire between A and B and confirm that current is going, in this whole scenario, current is going to want to flow from A to B. If the current's going to want to flow from A to B, A is going to be at higher potential. For that to be the case, I'm going to assume that the current is going right in here, going against the battery, hitting this and coming around and hooking right around. So the current goes from A to B, not B to A, but rather A to B. I'm making that assumption here. I'm saying for the 12-volt battery, current I1 fires right out. It's a big amount of current. We're going to say a relatively big amount of current, and current I1 fires right out of here, guys. So that's with the wire now. So you're getting a little different scenario of what's going on. I'd done this kind of cold the last time we did it. I'm still doing a little bit on the cold side, but kind of on the fly here. But I think this is valid stuff. 12V is this. Here you go. 12V, bam, fires out I1 straight into here, into this junction. I1 breaks up into I2 going down and coming around again. And so I2, I1 goes into here. I2 breaks off and goes here, and I3 goes straight out this way, goes all the way here, hooks around. I3 and I2 get together, and they merge, and they become I1 again. I1 equals I2 plus I3. I1 equals I2 plus I3. If you're going to go around this way, let's take a walk. From here to here is plus 12. You lose 2I1, and you lose 4I2, and it comes right back here. 12 plus negative 2I1 plus negative 4I2 equals 0. Conservation of energy, utilizing the principle of conservation of energy. Go here. I3 hits right into here. It's going against the battery. Potential drop of 4. Comes around here. Another potential drop of 10 I3. Going here, it's going from a low potential to a high potential pathwise, so it gains 4I2. It gains 4I2, loses 10I3, and loses 4 for this one right here. Lost 4, lost 10I3, but gained 4I2. 3 equations, ladies and gentlemen, and 3 unknowns. I plugged in I1 equals I2 plus I3. I substituted, wherever I saw an I1, I substituted for I1 by putting the sum I2 plus I3. I1 equals I2 plus I3. Yeah, I did that up here, and I got this. I left the other one alone, and I got that. I now have 2 equations in 2 unknowns. I divided the top equation by 2 all the way across, got this. Divided the bottom equation by 2 all the way across, got that. I added a -6 on each side and then multiplied by -1 on each side, got this. I added a +2 on each side and just left it like this. I solved these 2 equations in 2 unknowns and I got that. True. For the record, not really that it's necessary, but since we came this far, might as well say that's I2, that's I2, that's I3. I1 is the sum of these 2. I1 is the sum of I2 and I3. You add them together, you get 38 17 amps. Sorry, I didn't have room to put the amps here. It looked kind of weird, guys, the way it is, but you know it's amps. Okay, not a good place to put it here, guys. Here we go. I'll put it right there. How's that? 38 over 17 amps. That's 2 4/17 amps total. It breaks up like this: 6 over 17 amps and 32 over, 6 over 17 amps and 32 over 17 amps. They're all positive. They're all positive means the diagram we drew is correct. The diagram that we drew is correct. The currents are flowing as we have them depicted. And you can see up here somewhere, there's current, and down here somewhere there's current, but the current is tending to go from the location of A and thereabouts, down to the location of B and thereabouts, and then complete this, and then throughout the circuit, throughout the operation of this circuit, current is flowing from, periodically it's to be found located somewhere, wherever it is. Here's how the current's flowing, you guys. I mean, we got it. So at this point, I might as well draw it a little bit more. There's that. There's that. Yeah. From this vicinity down to this vicinity, that was our guess. We said that there was more flow of current. We said that there was the tendency for the current to flow if you connected something to it. The current was going to have the tendency to flow from A to B. And that's how this drawing depicts everything. As you can see how it depicts, look what the arrows tell us. As the arrows show us. Absolutely that's the case. A lot you can say there. I mean, as this is all proceeding, we got I3, we got 6 over 17 amps is how it's flowing for I3, and there's 10 here, there's 4 here. What's going on here? Where is this happening before that all happens? So you had a situation where I'm going to leave it just at that for now. And the way we calculate it, I think is acceptable. But I think this gives us more of a gut feeling for what's happening. When I was trying to do this the last time that we were together regarding all of topic 18, or at least regarding this particular, I was doing all of topic 18, or a lot of it. This one problem was the kind of the most disturbing, at least for me when we were looking at it. I'm trying to look at it a little more in a rather, like I said, just off the cuff way when we were looking at it. This confirms our suspicions, though, and what we had thought. A is at higher potential than B, and that would make sense as this whole thing proceeds here. You're looking at it, and I'm just trying to think exactly how we'd want to say something like this. You could say, you could confirm in a sense if you took the 4, as I do this on the fly, 4 times the I2, that's the gain in potential there. Let's see where this is going to go. 4 times the I2 will give you 128 over 17. 4 times the I2 is 128 over 17. Subtract 4 from it, and there's, and what's going on here? You're going to subtract 4 from it, and you're going to subtract this from it. You wonder if it's going to come out to be 4 as far as the potential difference there. That's another interesting point in its own right. Let's kind of look at it. I'm going to do this in my head first, and we'll take it from there. We did confirm a major point, though. The tendency is going to be from around here, current is flowing away from here to here. Gut feeling on the whole process is, A's got to be higher potential. Look how the current's flowing. I don't see current flowing from B to A. Instead, I see it flowing from A to B. And that's significant. So I'm looking at this, I say, well, let's kind of take a look at it, where it would actually go. We had said various things when we had done this. I'm looking at I sub 3. If I multiplied the I sub 3 by 10, I'd get 60 over 17. 60 over 17 take away, and then gain. So where's this? Where's the whole thing coming from in that regard? Where's that? How's that working? So 60 over 17, and then subtract. Right, 10 would be the 60 over 17. I sub 3 is 60 over 17 times this. It's a drop in potential of 60 over 17 times 10. It'd be a drop in potential of 6 over 17 times 10, which is 60 over 17 drop. So it's negative 60 over 17. If you gain here, so let's see what we could actually say here before you actually got that one. You could look at this 4, and that's the I2, 128 over 17, and that's a gain. So 128 over 17 plus a negative 60 over 17 is 68 over 17, which is 4. 4 and negative 4 is 0. Yeah, it's confirmed in that regard. This is the drop of negative 4 when you go through here. What is it before you get to the drop of negative 4? It's 4. From here to here was a potential of 4. Because that's everything else. The 4 that's here is going to get eaten up here. And you got that situation over there. So what you have is what was going on. All this right here has got to be a positive 4, because a positive 4 and a negative 4 is 0. Here is the aggregate of positive 4 right here. Well, where did that positive 4 come from? Well, it was negative 60 over 17 plus positive 128 over 17. is positive 68 over 17 is positive 68 over 17 is 4 volts. 4 volts are eaten up here. Where did they come from? They had to come from here. So they're coming, you know, what is able to do all this, for all this stuff that comes out here, this tells you what's going on before all this happens. I'm sorry guys, it's a little, I guess there's definitely more articulate ways to say this, but for you to go through this, it's a drop of -4. What's going on everywhere else? In aggregate, it's a gain of 4. In aggregate, before you get to the drop of 4, you gained 4. 4 and negative, you know, going this, remember how this is working, how this is moving, guys. As this moves against this thing, before you get to the drop of 4, for this whole thing to add up to 0, if this is -4, before you get to this, before you get to the -4, everything else has to be 4. And that's what's associated with that being 4. You're not going to see a problem like this. I'm not going to give a problem like this where, you know, this is a valid problem. If you actually if it was drawn right from the get-go to say, okay, let's draw a wire right here. And now calculate all the currents. Yeah, that's valid. The other question itself, obviously, 47 is also valid, but I think it can be more confusing than helpful for what we're trying to do in our class right now based on the level of difficulty that we're trying to do some of this stuff, you guys. But definitely that's where that 4 volts is coming from. It needed to be talked about. So here it is right here, guys. We'll talk about it. That's it. I mean, so there's mention of it here, guys. And it basically tells you that. Before, you know, with all the stuff going on, what is going on, since this is associated with all this, whatever these guys are doing is associated with everything else that's going, you know, whatever these guys do in aggregate is basically this whole run right before you get to that, which means what? Because these guys are live. I mean, everybody's connected, at least imaginary connected right here. They weren't connected initially, but let's say it was connected. Everything that happens is live. For this to be able to happen like this, you know, it's got to be at a higher potential for that to happen. There's no way this stuff can come through here and be something positive to add on to the negative for it to be 0. This in aggregate is 4 volts before you get to the -4 volts. Here's the -4 volts because you're going in that particular direction. Here's the -4 volts. It's got to be this. Everything around here has got to be in aggregate associated with positive 4 volts, and that's where that's coming from. Okay. You're not going to see it. You know, again, this is valid. If there was a real wire right here, hey, tell me what I1 is. Tell me what I1 is, what I2 is, what I3 is. Absolutely. Let's talk about power going through the resistors, something like that. I'm not going to ask you something like 47, but again, it needed to be talked about a little bit. When I had tried to talk about it in topic 18, I made an arithmetic error with the 10, and somewhere the 10, I think the 10 I had is a positive 10, not a negative 10, or depending how I had set it up, you know, positive 10 or negative 10, depending what the setup was such that I had the wrong sign. I had the wrong sign, so it was giving me different answers. And those answers were going to lead us to a bad place. So, I didn't watch the sign as I should. I caught it here, so we're good. All right, guys. So, just something to have in mind. Let's talk about a few things. If anything, it's a decent academic exercise. Some interesting mental gymnastics. to get us through what we need to do. So, chapter 19, topic 19. Let's talk about problem number 9. All right, guys, and didn't put the pages on there, but it's the pages associated with the 11th edition of the Serway book. That's page 648. Pages 648 to 655. Okay, all associated with that. Let's look at number 10. Forgive me, let's look at number 9 rather. Number 9, a proton moving at 4.0 times 10 to the 6 meters per second through a magnetic field of magnitude 1.70 Tesla experiences a magnetic force of magnitude 8.20 times 10 to the negative 13 newtons. What is the angle between the proton's velocity and the field for that to be the case? So the proton's moving with a speed v equals 4.00 times 10 to the 6 through a magnetic field of magnitude 1.70 Tesla. It experiences a magnetic force of magnitude 1.20 times 10 to the negative 13 newtons. What is the angle between the proton's velocity and the field? If the field and the velocity were perpendicular to each other, it'd have the maximum value of force. Perhaps they are perpendicular. My gut feeling is that's not the case, but we don't know that. I mean, we know this. We know that F vector equals Q vector cross B vector. Correct. As far as magnitude is concerned, QVB sine theta. If the sine of theta is at its maximum, then QVB sine theta is at its maximum for a given Q, a given V, and a given B. And for some theta that could vary, F is going to be at its maximum, and F vector is going to be at its maximum, consequently, because this just means what we know about the cross product already. We can get the magnitude of the cross product. Well, the magnitude of the cross product is this. And we know that, all things equal, if theta is allowed to vary, if theta goes to 90 degrees, which is pi over 2 radians, the sine of pi over 2 radians is equal to the sine of 90 degrees is equal to 1. That's going to give you the biggest answer. We don't know if that's going to be the case here. We do know this math right here. We know that, give me the angle where this is all occurring, or at least give me one of, there's a number of ways this can be argued, guys. You got to be kind of careful here when you're talking about angles. You got something like this, and this is theta, and this is 180 minus theta. The sine of theta is equal to the sine of 180 degrees minus theta. The sine of 70 equals the sine of 180 minus 70, which is 110. The sine of 70 degrees is equal to the sine of 110 degrees. And that's, so if theta was, like I said, 70, sine of 70, theta 70, 180 minus 70 is 110. The sine of 70 equals the sine of 110. All right, they're not really going there. They're saying, okay, give me the answer. The biggest it's going to be is 90 degrees. Go for the acute angle or the 90-degree angle that solves this, and that's basically how they want you to go about it. But again, be aware of the mathematical reality of what's going on. We know this is true. I think we've talked about, I've talked about this in numerous instances. It's hard to remember all the contexts in which something can get said, but let's say you go from 0 to pi or 0 to 180, and then goes this way. Well, if this is 0 and this is 180, and this right here is 90, if you got something here, you also got, if you got a height right here, guys, you also got that same height right here. They're symmetric with where this thing is. What do you mean? Well, if this is a length of theta from 0, it's the same length theta from this guy. It's theta away from here. Well, if it's theta away from there, 0 to 180 minus theta, if this departure from 180 is to the left theta amount, how big is it? Well, 0 to 180 is that. You can't be that big. You're going to fall short by theta. So it's 180 minus theta. This is theta away going to the left. I'm sorry, this is theta away. This is theta away going to the right, and this is theta away going to the left. And the symmetry is that. And that's where you're getting the answers. As we said, the sine of theta is equal to the sine of 180 minus theta. Okay, keep it in mind. There's some interesting conclusions that get drawn if you make some halfway decent drawings of what's going on here, you guys. So, to make a long story short, I guess you could say, they want the angle. Sine theta is F over QVB. And you're going to plug in all the appropriate values here. You're going to say, hey, they told me that. Make sure the values are in agreement with the system of measurement that is the standard. Doesn't matter what system of measurement you use, as long as the system, as long as all items involved, as long as all quantities are consistent with the system that you chose. If everything is consistent with the system that you chose, you're okay. Well, let's use the MKS system of units. F is 8.20 times 10 to the negative 13 newtons. Q is the charge on the proton, which is 1.6 times 10 to the negative 19. The speed is 4 times 10 to the 6 meters per second. And the B field is 1.7 Tesla. Plug all those in there and, grind out the answer. Well, what's it going to be? It's going to be sine theta. Theta is going to equal the arc sine, or the inverse sine, of sine of theta. And some of the talk we gave, 48.9 degrees, or go 180 minus 48.9 degrees. And I have these in the notes, guys. They're going to scroll. Or this, Get write it that way or the other, depending how it's moving in the field. It doesn't matter a whole lot. Depends where you want to, how the field is going. If the field is doing this, and the trajectory is this, here's your theta, the 48.9, and this is 180 minus 48.9. Which is this. This is the 180. The 180 minus theta, and this is just the theta, which is 48.9. Okay. That's how it solves, you guys. I mean, you got this guy. Well, look where the angle's made, you know. Here's where the trajectory is. Yeah, the trajectory was there and it went away that way. Here it's a pretty big opening. Here it's small. Right, the math is the math. It's going to be the same answer. The sine of theta is the same as the sine of theta is the same as the sine of the quantity 180 minus theta. So either one of these, this is theta, and this is 180 minus theta. And that'll get you there. So there's your answer, guys. Okay, that's 9. Let's go to 37. There's notes, and like as we said, there's plenty of notes on this whole process, guys, that you're going to have, to which you're going to have access. So 37 is saying an 8-turn coil, 37, an 8-turn coil encloses an elliptical area having a major axis of 40 centimeters and a minor axis of 30 centimeters. The coil lies in the plane of the page and carries a clockwise current of 6 amps. If the coil is in a uniform magnetic field of 2 times 10 to the negative 4 Tesla directed toward the left on the page, what is the magnitude of the torque on the coil? Hint, the area of an ellipse is A equals pi AB, where A and B are respectively the semi-major and semi-minor axis of the ellipse. So, pretty fascinating stuff in that regard. So A and B are the semi-minor and semi-major axis. So you got to be very careful here how they say this. They give you the major axis in terms, they tell you what the major axis is in terms of sine, and they tell you what the minor axis is in terms of sine. And so major is 40, major axis is 40 centimeters, and minor axis is 30 centimeters. Semi-major is half of the 40 centimeters, 20 centimeters, and semi-minor is half of the 30 centimeters, which is 15 centimeters. And it's pretty fascinating to look how you can actually prove the area of an ellipse. That's another problem. It'd be a neat problem to prove, and it's very provable. But it's, something pretty tedious. Not what we're being asked to do right now, but they're saying, at the end of the day, what is the magnitude of the torque on the coil? So that's problem number 37. So let's take a look at that. And we'll move on to 39 as well, right after that. So let's, anyway, I got my notes here the way I'm going to show it. Let me go pretty close to what they're talking about when I want to look at this, you guys. Now this is by no means going to be a good drawing, obviously, but here's an ellipse, and things wound up a bunch of times. There's a B field going this way to the left. They're telling us that the current is flowing like that. They tell us a lot of stuff, and they're helping us out enough. Like I said, if we really wanted to get rigorous about it, we'd prove why it's actually the way it is. This is 30 centimeters, major axis. So semi-major would be halfway across. Halfway across would be from the middle across. From the middle up is semi-major. From the middle all the way to the top, or from the middle all the way to the bottom is semi-major. From the middle all the way to the side, as it's configured here, is semi-minor. Yeah, I mean, it's the way it is. There's a number of ways this could be done. It's pretty fascinating proof to do it. That's not for us right now, guys. So let's kind of leave it at that. It would pertain, the pi AB is of great interest. How that would work out when you're actually doing this. You're deforming a circle, and you're trying to get the area of the deformed circle. You've deformed the circle into an ellipse. There's ways you can certainly do that. There's ways you can certainly look when you're trying to figure that out. So you're saying, it's kind of a crazy thing in its own right, I guess you could say. You could say that this is, there's a number of ways to do it. Again, I'm doing this sort of on the fly here, but if you got a circle, it's pi r squared. You'd have, like I said, you'd have, it's pi r squared, and you could say that, let me just speak the language they're kind of speaking to do this. I'm not going to go too greatly into this. Are respectively the semi-major and semi-minor axes. A is the long semi-major. A is the semi-major, which is the long one, and B is the semi-minor, which is the short one. So, and you could say, well, what is going on here? What has happened here? How would this work? Well, if you had this guy and he was at A height, and he's A long right here, right? And it's A everywhere. There are ways this is its own fascinating proof. Pi a squared, which is the same as pi r squared. That's its own. Proving this is not real difficult, but you can prove that. You can prove that A is equal to this. One argument for how that works is, for a circle, you'd say, okay, this is not rigorous by any means right now. If this was R, if the radius was R, let me just kind of give myself since we got here, we entered the dance, so to speak. We got to do this thing, I think. Looking at something like that, you got this guy is R in height, and it's R everywhere there. There's an infinitesimal length right here. There's another infinitesimal length right here. And basically, you're finding areas of triangles and you're adding them all together. Well, the length of this guy would be a base length of, let's say, B. And they all would have, the base length of B. And it goes just all the way around here. Let me add the area of all those triangles, and let me keep making the triangles with a smaller and smaller and smaller and smaller width. Well, isn't it true that when you look at that, B, this is R, 1/2 base times the height, 1/2 base times the height is that area. True. Let's say, true. That's for a triangle. Now, the triangle, there's a curve here. There's less of a curve that's seen the shorter the distance you're moving. I can walk 3 feet over here. The Earth has a curve. I don't really experience that curve very greatly. It looks like a straight line to me. If I was looking at something from a great distance away, I could definitely see a curve a lot easier. So you got this right here. That's 1/2 BR. Well, yeah. Add the number of triangles that are there. Well, as B, the base length gets smaller and smaller, you're going to need more triangles. True. Let's pull that B out of there. As B gets smaller, N's got to get bigger. If B gets smaller, there's more of these N's. There might be 10 of these triangles making up the sphere. 10 of these triangles making up the circle or close to it. Yeah? Why don't we use 100 of these triangles? It'd be a better approximation. I got a better approximation. Do 1 billion of those triangles. Yeah, B is really small, N is really big. Isn't the base length about the same length as the arc? And if you add all those arcs, and basically the base length is about the same as the amount of arc that's present. So the amount of arc that's here, and it's an equal amount of arc here, length B, amount of arc here, that's B, amount of arc here, that's B, amount of arc here, that's B, and that's where all this comes into play. It's B everywhere. This is obviously a horrible drawing, but if you add all those arc lengths together, you're going to get the circumference of the circle. Wait a minute. Put it at NB. Put 1/2 R right here. We said NB was the circumference of the circle. Half R is this right here. 2 times 1/2 is 1. Pi times R is pi r squared. It's kind of a gut feeling as to why that works. For the circle, pi r squared. Well, here it's pi a squared because a is the circumference. If n gets really, really big, b gets really, really small, but it just adds all the way around. And every one of those straight lines, any one of those straight line segments, gets closer and closer to looking like the arc and looking as big as, being as big as the arc length. And if you add all those arc lengths together, it can be nothing other than the circumference of the circle. Pretty neat stuff. Saw that in a textbook a long time ago. So they say some stuff to you there. All right. Well, great. Okay, the pi r squared is believable. Pi a squared is available, believable. And what do you think? Yeah, we said what we said. A good way to get yourself out of the woods with that. And again, nobody asked us this. They gave it to us. But I tell you what, guys. I mean, maybe it's just worth it. Here's your pi r squared we talked about. What do you say you leave the minor axis alone? We'll call it the semi-minor axis. And you somehow pick this thing up and stretch it. You still leave it with the height of A. You still leave it with the height of A. This is obviously this is a bad drawing. I mean, let me see. Let me try this again. Man, this sure looks like more area than that. This sure looks like more area than that. Even if the height right here is A. Yeah, it is with the other one too. Yeah, the height right there is A, you guys. But this guy right here is B. Or you could do a lot of stuff here. Let's see. Okay, this is true, guys. Let me try to stay consistent. They call this, since A is going to be the short guy, let's not call it A. Let's call it B for the semi-minor axis. So that's going to be for this one, the small one. Okay, pi r squared. Let's just call it B. No big deal. I'm going to call that the minor. Semi-minor. And this right here is A. It's longer than that. If you were summing all the area, if you're like taking slices here and making the slices smaller and smaller and smaller and smaller, if I'm doing all this, getting all these slices here, slice from here to here, slice from here to here, and everything in between, guys. I don't, if I just take it as we go across here, if I add all the slices, I'm going to get this because it comes from that. True. If you did the same number, it's very, very many slices. And in the limit, it's a calculus problem, it will be that area. But so you make the area as big as you want. I mean, you make the slices as small as you want, as narrow as you want. Let's keep doing that. Let's go, and again, this is not a good drawing that I've drawn here, but it's the same thing here. Let's do this. Let's come over here. And let's say I do the same amount of slices. You think you can do the same amount of slices? Yeah, I think I can. Tell you what I mean. I did 100 blue slices right here, each one of which is, how thick is each slice? Well, if this is B, if this is B right here, and that's B right there, that's 2B divided by 100. That's how thick each slice was. 100 slices. This one, I also did 100 slices. And it is, the way it plays out, I'm gonna find it in such a way that I'm gonna have the same height B, and it's gonna taper off in such a way. So basically, it's like the ellipse is a circle that's been stretched, in a sense. It's a circle that's been stretched, And all these values here, all the values on the circle, all these heights right here, all these, I don't want to write too much here, guys, but all the heights on the circle are also present in the ellipse, but they're spread out. How are they spread out? Well, there are 100 of these. How thick are each strip? How thick is each strip? It's 2a over 100. If I had 1,000,000 of these strips, I'm not going to call it 2b over 100. I'm going to call it 2b over n, and n goes toward infinity. That's how thick each strip is. And these aren't as thick. They're 2a over n. And it's the same exact height. I'm going to find there is a height. It drops off more slowly, but I can find this height. I can find the height right next to it, but it's occurring somewhere else. And it's simply equal to that. Well, wait a minute. If each of the strips is wider here for the ellipse than it is for this guy over here, how much wider are they? (2a over n divided by 2b over n. Man, I wheel and deal with that. The ratio is a over b. Each strip is a over b times wider here, but has the same height as those have. I can hit the same exact height when we do this. I mean, it's simply been stretched. What used to go on over here, if you take something here and find out where that height is, the other one is going to be occurring somewhere else, but all of these are going to be occurring. Each one of these is a over b times bigger. So the area, all the small areas here, when added together, give you this. All the same number of small areas with the same heights, but more broad base added together, gives you something bigger. What though? Well, each base is that much bigger. So if I add all of these together, you got the summation of all the areas, summation of A1 plus A2 plus ... plus A sub n is equal to pi b squared for the first one. Pi r squared, which is pi b squared for us. Yeah, pi b squared, huh? The other one is going to have the same areas, but they're going to be a over b times a1. A over b times a2 plus ... plus a over b times a sub n. And let's talk. Why don't you pull... That's all distribution. You're summing all these. It's the summation of all these. The summation symbol is a little on the redundant sign, I guess you could say. There it is. You got this. They add up to pi ab squared. Yeah, that's true. Do me a favor. Pull ab out of there and got a1, a2 plus wait a minute, this A1, A2 plus dot, 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 A sub n is pi AB. Yeah, I'm sorry. Forgive me, I jumped the gun on that one. So this is the small area. And we said an ellipse is just a distortion. And it's a distortion that's proportional in that regard, in the regard that we said. If you really wanted to see the size of something regarding this, so we'll talk more, but we got this. Yeah, that's the small area. A1, A2, A1 plus A2 plus dot, dot, dot plus A sub n equals pi b squared. Agreed. For the thing that's been stretched, called the ellipse, all the heights are the same. The base areas are the base areas. I'm sorry. All the heights are the same, but the base areas are A over B times bigger than what the other ones were, because they're broader. If they're broader by a ratio, if the width of the small rectangles taken to the limit, if the width of each one is always at a ratio of A over B times bigger than the bases of the smaller figures, rectangles, the circle's rectangles are smaller by a factor of B over A. Put another way, the larger figure, the ellipse's rectangles, are larger in terms of area by a factor of A over B, because you got to stretch the base if you're going to use the same number. If you're going to use the same number of rectangles for both figures, the one that is broader is going to have rectangles that are proportionately broader as well in terms of the base length, in terms of the width. By how much? Well, if the whole width of the ellipse is larger than the width of the circle by a ratio of A over B, each rectangle has to be larger by a width of A over B. So you put the A over B right here for each one of these. So this was for the circle, this is for the rectangle. This is for the rectangle, and there's a lot to say here, and maybe I shouldn't have. We have this. Yeah, we sure do. This right here is pi b squared, and that A over B is A over B. Here's A over B times pi b squared. Wait a minute. And that's the area of the large one. A over B times pi b squared equals pi AB. And that is the area of an ellipse. Hello everyone again. I had to take a little bit of a break, and I'm inserting this into one of the problems. It was into part of the problem that I had done. It was the problem that involved the elliptical area, problem number 37 from topic 19. So from topic 19, problem number 37, I did some extra stuff. So this is going to get fit in here, so you're going to see it cut in there a little bit. I had attempted to show something. I was more or less going in the right direction, but I made a careless mistake, so I obviously don't want to include that careless mistake in the explanation. The argument was going essentially in the right direction toward the end of the whole process, but again, there was a careless mistake made, and that's certainly my fault. So this right now, as you're looking at it, is kind of a correction of that. Now, as this is united to the actual problem, everything that led up to the problem was fine. We made the assumption, with everything leading up to the problem, that if you looked at a circle, the area of a circle is pi r squared, where r is the radius. Well, if you called the radius equal to b, then pi r squared for the area of a circle is pi b squared. So b's right here. Doesn't look a whole lot like a circle, not the greatest drawing in the world, but let's call it a circle. I labeled it a circle. So the radius r is equal to b. So pi r squared for the area of a circle is pi b squared for the area of a circle, pi b squared. Now, if I wanted to find the area of an ellipse associated with this circle, and I'm going to stretch the circle sideways in the x direction, and remember now, this is b radius everywhere. B going up high, b going sideways. Well, let b going up high remain as is, but let me stretch this sideways from a length of, b plus b, from b here and b there, to a length of a plus a. In other words, the b gets stretched from b to a. Over here, the b gets stretched from b to a. So it goes from b plus b, which is 2b, to this being stretched, and it's a plus a. So it gets stretched to a length of a in each direction where the b stays the same. Leave this alone right here on the side. I'll come back to that. We said when you do that, it's the exact same circle, but same height right here, but it got stretched this way. We justified in the earlier argument, and that argument stays. There was nothing wrong with that. So you're going to see this basically spliced into the argument that I did last time in this problem. We're going to try to carefully splice this into this for you to look at, and then so it should be fine. So as we splice it into this, we did make the argument that if you keep making strips right here, n number of strips here, and you make the same number of strips here, n number of strips here, well, okay, you got n number of strips that we've drawn in the past, and you saw that, and we have a record of that in the film. We saw how we did that, but we argued the n number of strips here have a base width of capital B. For you to be able to fit perfectly the same n number of strips over there where it's more narrow, because the circle sideways is b plus b, it's 2b. For me to fit all n strips in here they are. Each strip has a base width, there's a height associated with it, but it's got a base width of capital B, as you've seen me talk about, or a base width of whatever it's going to be. Whatever the base width is, we know that. Okay, there's a base width there, and we got n of those strips. Each strip is going to look a little different because this strip right here is not going to be, this strip's not going to be that long. This strip's going to be longer. This strip's going to be longer still, and et cetera, et cetera. There's n of them, and they're all right next to each other, and they got, let's just say, for the point of argument, a width of b. Now, I've used capital B before when I was getting the area of a circle, and we did those things with the triangles, and that's still on record. But let's say it's a capital B here, as far as width is concerned, or whatever it may be. Let's say what that is. So it's a width, the same width for each one, and there's n of them here. Well, this one's a lot broader, so if you're going to perfectly fit the same n number in here, each base area has to be wider. If each base length, the base length B was the base length for each of these guys right here. Say right here, as far as what that might be. Base length B, yeah, right. But for the other one, if you're going to fit all n of those in there, and this thing is broader by how much? We said it was broader by the ratio of it's A plus A, that's 2A. This guy right here in width, total width, is B plus B, that's 2B. And as we said, this was A plus A plus A, that's 2A. So 2A over 2B, the 2's cancel, you got A over B. The width of this guy has got to be broader. Each tiny slice has to be A over B times bigger in width. Each tiny slice has to have a width A over B times the size of the B over here. This is B, but you know, for each one of these, but if you start slicing here, it's got to be a little bit broader. It's got to be a little bit broader. So what you're talking about here, this would be A over B. This would be A over B times the capital B as far as how broad this is. A over B times capital B, as opposed to this guy, which is just B. If I'm going to fit perfectly, or very close to perfectly, n number of slices looking like this, n of them without any gap between them, one on top, one right next to the other. If I'm going to fit n of them here, each one here having a base width of, let's say, capital B, then to fit exactly the same number of n there, you got more ground to cover. You're covering a ratio of 2A over 2B times the size of what's going on over there. A over B times more length you have to cover. So each individual base length has to be A over B times the size as the one that was over there. B was over there, A over B times B would have to be the one that's here. A over B times B would have to be the one that's here. Well, if you add them all together, you can factor the A over B out, and you saw me do that in my argument. I did it in a little, perhaps different notation than what I'm using here, but that's neither here nor there. You can factor, you can factor the A over B out, as we said, and the area, if each one of these has a broader base than the base over there, this broader base is A over B times the size of the smaller base. A over B times the size of the smaller base is the base here, and it's for each one of those. If it's for each one of those, we can factor, when you're doing the sum of all those areas, you can factor A over B out of there, and it's A over B times the area that you had over here. The area here was pi B squared. The area here is going to be pi B squared times a number bigger than 1. It's going to be, the area of the circle was pi B squared, but this is going to be A over B times the size of pi B squared. It's going to be A over B times the size of the circle. It's going to be A over B times the size of the area of the circle, because each one of the slices here has a width that's A over B times bigger than the width of the circle. Every slice associated with the ellipse is A over B times the size. It's A over B times the size of the width. Every width of each slice, every width of each and every slice associated with the ellipse is A over B times the size of every corresponding width of a slice of a circle. It's A over B times bigger. So you factor the A over B out of there, like I showed you in the earlier notes. You go A over B times pi B squared. A over B times pi B squared is pi AB. And that solves the problem. There was one sticking point, and that we got to look at. We say, okay, you're corresponding them like this. Can you guarantee that this guy right here, wherever it may be, can you guarantee that that guy right there is as big as, wherever that may be, right over the circle, guys. Can you guarantee it's as big as this guy exactly in the corresponding place? I mean, are you getting the same y values? if this is a y value, and down here is the same magnitude y value, it only happens to be negative, but if this is a height of 10, and down here is a depth of 10, 10 plus 10 is 20, I would add the y here, and I would add the y there. I just double the y to know how long each rectangle is. Well, yeah, I can know how long each rectangle is. The big thing is the length of each rectangle, which corresponds to the size of y. If y is the same here, happens to be 10 big, and it's the same as this one right here in a corresponding place, happens to be 10 big here, it's okay. Is there a correspondence as you move along? Well, this gets a little crazy because and this works because of the symmetry. It's going to work on either side. If I can prove it on one side, and I can prove the height is the same. If I can prove that this height right here, y, is the same as this height right here, y, in a corresponding way. Now look, this guy went x over from the origin. This guy's going to go further than x over from the origin because it's been stretched out. It's not going to go x over. It's going to go a over b times x over. That is what the ellipse, that is what the x sub b is. The x sub b, the x associated with the ellipse, is going to be a over b times the size of what the x is. So in other words, the x from here to here is a walk of x to give you the climb of y. From here to here is a walk of x to give you a climb of y, and there's also a fall of y over here, so y plus y is 2y. If I can get the y's to be equal, I know that if I double the y's, I get the whole length of the strip. I get the length of the strip that's under consideration. So if you walk over x, there's a climb of y. Okay, I want another climb of y, but I'm not going to walk over x. I got to walk over a over b. I'm not going to walk over x, that length, like right here, which was associated with the circle. I got to walk over a over b times x, and that'll give me the climb of y. That's the only way it can work, guys. There has to be symmetry. The scale of this thing going sideways has to be that all the x coordinates are a over b times, all the x coordinates are a over b times the corresponding x coordinates in the circle. The corresponding x coordinates in the circle, when multiplied, the corresponding x coordinates of the circle, the x's, the corresponding x coordinates in the circle, when multiplied by a over b, means you're stretched out. Yeah, the whole ellipse is stretched out. The corresponding x coordinates, any x coordinate in the circle, any x coordinate in the circle x, any x coordinate in the circle x, when multiplied by a over b, moves you further out, but for the equation of the ellipse, it still maps you into a height of y, the same y over here. This way you're guaranteed to get all n slices in here. How big is n? The bigger you make n, the better approximation you get to the area. It becomes a calculus problem. It's absolutely a calculus problem at that point. The more you make, the bigger that you make n, the thinner the slices become over here by the circle. Yeah, the thinner the slices become over here by the ellipse, but the slices over by the ellipse are still, each one of them, no matter how small they are in both places, the slices over by the ellipse have a width that is a over b times what the slices are over there in terms of width. The width of the slices by the ellipse are a over b times the width of the slices over by the circle. A over, no matter, you could have a billion slices. Wow, that's pretty small. Well, yeah, it is really small. Let's call each width of a billion of those slices, each width is, we'll call it capital B. It's awfully small. True. There's a billion over here, that's awfully small too, but each slice has a width that's A over B times the size of the slices associated. It has each width associated with the slices in the ellipse have a width which are A over B times the width of the slices over by the circle. That's crazy. That was the premise. That was the sticking point. Well, that's a hard thing to prove. Can you prove that that's actually the case? Well, we're making this claim. Tell you what we can do. I mean, we can look at, now this was kind of where I ran into a problem the last time. The problem itself that they give us, and they don't even ask us to do this, but I think it's for your personal enrichment and for thinking this stuff out. It's very important to really be able to let your mind really exercise the mathematics of what's going on. There's less chance you're going to make a careless mistake if you're cognizant of a lot of mathematics. So that's my justification for it. For problem number 37, the ellipse is vertically oriented. And that's why I got in a little bit of trouble. I was trying to do it with a vertical, it was a vertical orientation, and I somehow associated the letters with vertical orientation. Well, it is vertically oriented. I just put it sideways. I put it sideways just to find the area. I thought it was easier if we move left to right. If we move in the horizontal direction on the x-axis, it'd be easier to find an area. So I took the vertical orientation, and I took the vertical orientation and I rotated it 90 degrees, and I put it in a horizontal orientation. The A being the long length that we had that was up top. A was the long length. A was associated with the major axis, and B was associated with the minor axis. Now the major axis is associated with the horizontal, and the minor axis is associated with the vertical, but it's going to be the same area. But if that's the case, you're going to have to call A, the major axis, associated with the x direction, because I rotated it this way. Okay. When I was attempting to do this at an earlier time, I made the careless mistake of not doing that, and the letters were getting kind of confusing. So this is why you're seeing this right now, guys. X sub b, that's the coordinate associated with the ellipse. It doesn't have anything special associated with it. I'm just labeling it x sub b because that's what's going on with the ellipse. In other words, what an x coordinate would be on the ellipse. I just labeled it x sub b. X sub b squared over a squared plus x sub b squared over a squared plus y squared over b squared equals 1. This is very derivable. We're not going to go there, I promise, but it's very much derivable. An ellipse is the set of points that are located somewhere such that there are two foci, and from those two foci, the distance to each point on the ellipse, the sum of the distances from each of the foci adds up to a constant. There's two focal points in a sense, two foci, and from there you can draw a point on the ellipse. In other words, wherever these points are on the ellipse, that point to one of the foci, that length, and that same point to the other foci, that length, when you add those two lengths, they're always a constant. Well, the points that satisfy that are this thing called an ellipse. And you can prove that. It's a bit tedious, but it's not really difficult. It's not very difficult, but it is a bit tedious. But you can certainly prove this reality. Okay, that's another story, but it can certainly be done. And once you've proven this, once you've shown this, and it's not incredibly difficult, like I said, a little bit tedious, once you get to here, let's see what the ellipse looks like. Well, here's what it looks like mathematically, or at least writing with an equation. Let's solve for y squared. Let's solve for y squared. When you solve for y squared, you subtract x sub b squared over a squared on each side, and you multiply by b squared on each side. Then you multiply the b squared all the way across, and you get this. True story. So if that's true, this is associated with the ellipse. The circle, this is b squared equals x squared plus y squared. Solve for y squared, you get y squared equals b squared minus x squared, and that's this right here. Now, look guys, we want y to be the same. We want to always get the same y value. Why? Why do we want to get the same y value? Because the y value is the half height of the slice that you're doing, and then if you double it, you get the whole length of the slice that you get. Well, if the y values are identical, you have a positive y value and a negative y value. We get that. The y squared, if the y squareds are equal, the y's are equal in terms of magnitude. So when you double them, you get the right answer. So let's make, if we get y squareds to be equal, if we figure out how y squareds are equal, we're good. You know, at least get the y squared is equal. We're trying to find a way to say that this y squared is going to be equal to that y squared. Wow, they almost look alike except for this. Man, that looks a lot like this ratio, a over b, only it's the reciprocal of it. What's going on here? Well, I'll tell you what. The only way these two guys could be equal is if this and that. This and all of this are, if these two guys are equal, it's going to work. It's the only way it would work. Then I could get them to be equal. I mean, you got the minus here, but it's a minus in both places. So how can I get this to work for for that and that to be equal? Set them equal. Square root each side. We don't care about plus or minus. We know from the symmetry of it, we're set. We're set. This thing's symmetric on both sides. When they square, they're going to go to the same place. So if we can just generically get this, we're okay. Let's just argue, around that point. Everything's going to work out fine because of the symmetry. Square root each side, just leave the primary root, and let's just see what happens on the right side of both these figures, the circle and the ellipse. Square root both sides, x equals b over a xe. Okay, interesting. Solve for xe. Multiply by a over b on each side. That's huge. Didn't I just say that? Didn't we just say that? That whatever location you got on a circle, you got to multiply the location on the circle by the bigger number, length of semi-major axis divided by length of semi-minor axis. This is bigger than that by definition. They're the same. When A and B are the same, you got a thing called a circle. The ellipse becomes a circle at that point. Then x becomes x of b. They're not stretched out. Those strips are the same width. Each individual strip is the same width for both circle and ellipse if the ellipse actually becomes a circle. But right here, for any walk of x that you take to the right, you'd have to go length of semi-major axis divided by length of semi-minor axis, a number bigger than 1. For any walk of x that you take with the circle, you have to go a over b times that walk for the ellipse for you to get the same height. And that's where this came from. And that's where the a over b times x gets you there. It's proven. It works. The earlier things that we did when we talked about, hey, because this proves that every base area here is a over b times the size of every base width here of a strip. Every base width of a strip here is a over b times the size of every base width over there. Because of this, when you actually do a subtraction to get the points here. In other words, if you basically go xe, xe2 minus xe1, you get delta xe. Okay, that's the base width. Isn't that right here a over b x sub 2? The x sub 2 is associated with the xe sub 2. So xe sub 2, x sub 2 and xe sub 2 are associated with each other. Minus, so this guy right here, so x sub 2, and we said you got to make it bigger. You got to make it a over b times the size of what it was. Then a over b times the size of what this guy is. What's going on here? You can take the a over b out of there. You got x2 minus x1. Wait a minute. That's a over b delta x. Wait a minute. The delta x is the width of the base. The delta x is the width of the very small base. The delta x is the width of the very small base of the circle. I'm sorry. The delta x is the width of the very small base of each strip that you're using to find the area of a circle. If you multiply it by a over b, you're getting this. You're getting delta xe, the change This is the width of every base length. This is the width of every base length of every strip associated with the ellipse. Every strip associated with the ellipse has a base width of delta XE. Yeah, that's equal to the width of every one of these strips in the circle times A over B. This guy's going to have a width, which is A over B times the size of delta X. It's going to be A over B. It's going to be bigger to a size of A over B times delta X. It's A over B times the size of delta X to get delta E. That's the justification. And as you move like this, you know, the x sub 2 maps into a y squared. The x sub 1 maps into another y squared. And correspondingly, the A over B x2 goes to the same size. In other words, so x sub 2 will map into something up to here. Sure, x sub 2 will map into something. If you multiply it by A over B and plug it into the equation for an ellipse, it'll also map into something that high. Over here, it'll be further away. It'll be A over B times x, as opposed to, it won't be a distance x. It won't be a distance x. It'll be a distance A over B times x, but it'll have the same height y. You got to have the rectangles the exact same size if you're going to do a comparison like this. The rectangles are the exact same height, that's for sure. They're all the exact same length, but the only thing different is every base width is A over B times the size of every base width over there. And A over B, so the whole area is going to be A over B times the size of what it was over here. Well, what is A over B times the size of what it was over there? That's where you're getting this. Okay, that had to be rotated over. I hadn't done that the last time, so I needed to get this done for you this time. Pretty fascinating stuff. This can be proved without great difficulty, but it is rather tedious, but we can still do it. We can still do it. So you know it's there, you're taking it on faith that it's actually true, and it's looking pretty good that way, guys. Let me see that this is actually showing up pretty good here, and it is. Okay. We're looking okay, guys. So, wanted to say that. We're going to put this into problem 37, and we should be okay in that regard. If you're on the ellipse, you got to walk further because the ellipse the ellipse reaches the heights at further off locations. So if you walked x, if you were on the circle and you walked from the origin, x away from the origin to reach a height of y, to reach that same height of y on an ellipse, you'd walk from the origin not x units, but A over B, where A is the semi-major axis length and B is the semi-minor axis length. On an ellipse, you'd walk not x, as you did for the circle, to reach the height from the horizontal axis of height y. You walk the distance x. For an ellipse, you would walk the distance not x, but the distance which is longer, called A over B times x. So you'd walk x units from the origin on the circle to reach a height y. To reach that same exact height y on the ellipse, you'd have to go further away from the origin than just x. You'd have to go to A over B times x. And that was that whole discussion, guys. And if you do that, if things are set up in that manner, then yeah, it'll be fine. And actually, finding the area works like that. So I just thought you needed to know the area of a circle, the area of an ellipse. I think it can only help you guys. It can only help you. The more we know, the better off we are. Given all this, what is the torque, you guys? What's the torque? What's going on? Well, it's not too bad. I mean, they're telling us with this that B times, the derivation here is its own interesting thing. Let's not go too crazy on this. I think we've gone pretty far as is. But basically they're saying this, how the angle hits. Well, it hits straight out at a 90-degree angle, so that's not too bad in that regard. You got this thing right here, you got the center right here. You can figure this thing out, and there's some really fascinating arguments here, guys. They pertain to area again, but let's not go there. What is going on? We know that if there's a current and there's a B field, a current is a bunch of moving particles. The current's I and the B field is B. Didn't we say that force was equal to QV cross B? Well, wait a minute, we've made it 90 degrees here. It's as though all these guys are the Q. Well, Q times V is a lot like charges going over a distance. The distance covered by a charge. Here's a charge. Here's one charge out of very many charges. Here is effectively what amounts to a charge or group of charges, amount of charge. There's an amount of charge. It is throughout the length of something, the amount of charge, or in our case, let's say just one charge moving velocity v cross b vector. Right. Tell you what, if there's a whole bunch of charge, then you can just say, look, all of that charge, there's an amount of charge that passes a certain point, and then a length L later, that same amount of charge passes that point. So there's an amount of charge, and there's a length of something we're considering, and there's an amount of charge, and it's essentially we are seeing a certain amount of charge go through a cross section, and then 10 seconds later we saw the same amount of charge happen there. Well, how did that all work? There was an amount of charge going through there. You could basically say that this amount of charge passed through one place. 10 seconds later, it passed through another place, L away. So in 10 seconds, it's as though this charge went from one place to another. Sure, but you can write it like this. Why don't you take the T and put it under the Q, and that becomes I times L. And that looks a lot like QV. QV looks a lot like this. If this amount of charge passed a cross-sectional area, and then I just saw it, and then 10 seconds later I saw it pass another cross-sectional area. What's going on here? Well, the amount of charge that's passing one particular place, it's also passing it at another place. We'll just say it covered the distance L, even though all that charge has saturated the place. Let's just say the length at a particular length, L amount of charge has gone through there in a time t. So you can write it like this. Well, wait a minute. Isn't that, can't you kind of... So you got Q over T L, that's IL cross B. Absolutely. That's the force. If I is right here, let's put I right here as well. Let me maybe use the same color, guys, doesn't really matter. Here's the I right here. It's a really weird thing, guys. It's a hard argument, and I don't want to, I fear I'm glossing it over in a sense. The amount of charge that goes through a cross-sectional area, well, that's the same as saying a certain amount of charge at a certain amount of time, let's say, you could say that it depending on the length of the wire under consideration, if the wire is saturated with the flow of electricity, if it's a very long wire, you can kind of assume that, wow, it's covering from one point to another, the wire under consideration, it's covering how much? Well, it's covering the amount of charge that's there per unit time times the length. So over a shorter length, it's as though that same amount of Q is not covering as much ground if you're just considering that length of charge, that length of wire. But the longer the wire and it's saturated with that same amount of charge per unit time, you can almost assume it's just a charge going very, very fast for it to cover that entire length. Sort of a bit of a hand-waving argument on that, but it's valid. It works when you're considering that. And it's valid for the forces. If it's a long wire and it's saturated with charge, a very, very long wire, it's as though X amount of charge is moving very, very fast to cover all that length of wire. If it's the same amount of charge per unit time, the same I, but we're only considering a short length there, it's as though it's the same charge, but it ain't going as fast because I'm only considering that wire. The more wire I consider, the more force that's associated with it, and that would be consistent with this. So it's an interesting ploy that you can use. It works. You might have another way to look at it, and please go ahead and do so if you feel better about that. But if this is QV and this is cross B, this is QB, this is QV and this is B. QV cross B, bam, the force is pulling this way. So right here, QV cross B, force comes out. Great. QV cross B, force comes out. It comes around here. The B is going this way. The I is going this way. QV cross B into the board. QV cross B out of the board. Out of the board? Yeah. QV, which is the I, right? For our purpose and the length that's associated with it. This becomes a calculus problem again. We're not, it's not bad. It can be done. Not our business right now. Let's just kind of look at it as QV cross B. QV cross B, right-hand rule. QV cross B, thumb into the board, the force goes that way. QV cross B, force comes out. This thing torques this way completely. And it's given by this. It's given by this. I didn't really ask, but for the heck of it, they tell us magnitude of the magnetic moment is IAN. Makes sense. A lot of turns, a lot of area, a lot of current, a lot of magnetic moment, a lot of magnetic dipole to look at it. Okay. Well, okay, great. I mean, I kind of sort of answers it. How many turns you got? Well, the turns you'd have to put the turns right here. You're going to have more. This is going to be happening n times more. Look at what I just did right here. This I, if it happens for one turn, when you got n turns, capital N turns, it's going to happen n times I times. N times I times. It's as though you're covering n times the distance. And there's going to be a greater force. So they go like that. So we look at it. Like I said, guys, when you don't, if you're comfortable with certain things, or You don't need to look at the proofs I gave for areas and stuff and how the mathematics works. Though it is useful, I think. It's pretty fascinating stuff. If you don't like it, please fast forward. Go a little bit forward, go forward, look at the stuff that is going to work for you. But use all the technology features that you have at your disposal, and the materials there at your disposal. Hopefully it can be of use. And that's what they're trying to say here. There's got to be an N here. I didn't have the N there initially. Usually the N is a 1, and I assumed it was just a 1. They're 90-degree angles. Well, that's its own kind of dynamic. Yeah, you can. Sure don't look like a 90-degree angle, does it? We're not gonna open this can of worms, guys. I just want to tell you something, just for the record. Sure don't look like it when it's taking a turn, does it? Yeah, it does. You can play the infinitesimal game I did with the areas earlier. We're not going there, but even here there's an application. Even here there's an application. You can make it so that when this is going like this, when the angles are under consideration, you can make area segments. You can make current segments that matter be straight up and down. Well, what about sideways? We're not going to worry about sideways, because sideways is 180 degrees. The sine of 180 degrees is the same as the sine of 0, which is equal to 0. It wouldn't contribute. So even here, you can kind of pretend that infinitesimal looks done the right way are perpendicular to the B field. There's I everywhere, and there's components of it. There's right here, nobody's going to argue this is completely vertical. There's a component this way, there's one that, this is what it is. There's a component that way, and then there's a component down, and that's the one I care about. This one ain't going to play the picture. They don't really tell you that, and so let's not even go there, but that's big stuff. So you look at this. Plug it in here, guys. What do we got? This is N turns. B field, 2 times 10 to the negative 4. I, 6 amps. Area, here we go again. Let's go. 40 centimeters is 0.4 meters. 30 centimeters is 0.3 meters. Didn't we say it was pi AB? Yeah, we said that ad nauseum, actually. We don't need to revisit that one again. It's going to be pi, area is going to be pi times 0.4 over 2 times 0.3 over 2. So you got 8, 2 times 10 to the negative 4, 6 amps, pi times 0.4 over 2 times 0.3 over 2. There it is. There's your torque. Torque is such that the left-hand side moves toward you and the right-hand side moves away regarding the loop. We know that. We did this. There it is. And the notes are there, guys. You don't have to, like I said, some of the arguments I do that are extra, that are extra, you're not going to really, you don't necessarily see them in the notes, and all the notes that I do. The stuff I did with the area, I just figured it was very interesting to look at it. But that's your call. It's not going to be something that you're going to get tested on. They're going to give you the area, and you're going to work with it. And that would have gotten us there. Just wanted to give it a little bit different of a look as well, if we could. That was 37. 39. 39, a 6-turn circular coil. Forgive me 1 second here, guys, if I could. For 39, a 6-turn circular coil of wire is centered on the origin in the XY plane. The coil has radius, it's circular now, guys, we said. The coil has radius R equals 0.200 M and carries a counterclockwise current I. I equals 1.60 amps. A and B, guys. A, calculate the magnitude of the coil's magnetic moment. B, find the magnitude of the magnetic torque on the coil due to the 0.200 Tesla magnetic field that is directed at an angle of 60 degrees from the positive Z direction. From the positive Z direction, it has components only in the XZ plane. Okay, I'm going to try to draw this, try to make it look halfway decent. I think we should be okay, guys. I think it's not too much of a problem here when we look at some of these. Okay, the drawing in the book is in very much all likelihood going to look better than any drawing I'm going to make, but let me try to put something together here. Okay, they're telling us that the B field lies only in the XZ plane. So let me try to do something here. Make an angle. Now here's the Z. Here's axis Z. Here's axis X. This is theta. They're trying to, they do some stuff here that we got to really kind of watch out for. Here's that, and here's this. And I did warn you, this is going to be, the way I draw it's going to be a joke, but and then this, and then the coil lies in the XY plane. A 6-turn circular coil of wire is centered on the origin in the XY plane. It's hard to know how to. Okay, that looks maybe a little better, look more perspective maybe. There's current I. This is R. There's the Y. Theta 60 degrees. Okay, they're saying a bunch of stuff here. They're telling us what it is. Find the magnetic moment. Basically, guys, it's a 6-turn. It's a, the thing in red that I just drew. The thing in red that I just drew lies in the XY plane. It's a 6-turn circular coil of wire. It's centered on the origin in the XY plane. So it's in the XY plane. The coil has a radius of 0.2 meters. R equals 0.2 meters. Carries a counterclockwise current. And while we're looking at it, as we look straight down on it, it carries a counterclockwise current I of 1.60 amps. A, calculate the magnitude of the coil's magnetic moment, and then find the magnitude of the magnetic torque on the coil due to a 0.200 Tesla magnetic field that is directed at an angle theta equals 60 degrees from the positive z direction. Angle theta from positive z direction. It has components only in the XY plane. So it's not really directing itself any other way. It's in the XY plane. So it's interesting how they're saying that. What do they mean by that? The B field I'm assuming is everywhere, but it's something that is associated with orientation. If you're looking straight down on it, you see a line doing that in the XZ plane. So, okay. This is easier done than said, guys. It should not be too bad. What they're saying. Okay, we've been there, we've seen that. This is the magnitude of the magnetic moment. Makes sense to me. If I is big and A is big and N is big, mu is going to be big. Sounds good. You plug in. 1.6 is the I. Pi r squared. They gave it to us in meters. We got to be faithful to the units. Number of turns, 6. Mu equals 1.21 amps We've been there, guys. We know how to go. We know how to go here. It's a 60-degree angle. And you know what? We're going to use that 60-degree angle. We're not going to have to modify that. This thing's on the ground. The area is perpendicular. It's a very good question in its own right, isn't it? The vector's doing that. The movements are there. Yeah, it's to be assumed this green thing is everywhere present but oriented in some sense associated with the X and Z axis. It doesn't have to be on that X and Z axis completely. It's essentially, it's all over the place and it's in contact with this whole thing in totality. Fascinating matter in its own right, how this can be actually viewed. So you look at it and you say, okay, well, if this is, if I'm looking down on this thing and it's shooting up that way, then I cross B, See, it's coming up. It's on the ground, and B vector is coming up this way. So papers are down. The C's here, so the papers are down. That's where the circular coil is located, coming up this way. Let's kind of pretend this square is a circle, and let's look at these flying out here. If you're looking at it like this, and it's going not clockwise but counterclockwise, A cross B. So let's see exactly. So it's doing something like this. On the other side, it's almost fascinating question here. You got the B here. I vector cross B. It's going that way. First impression on it, just looking at it, trying to see exactly. It's got to be some different look here going on. If you're looking at the board, let's say even here, let's say the circle's here, you're looking at the board and it's coming out, I vector cross B, man, it sure let me see exactly. I mean, I just don't want to write the notes down, guys, and try to throw it right by you. They're saying the magnitude of the torque is this, and I'm just having an issue of what they're actually saying. Yeah, I almost want to give an argument that I don't want to say, actually, so I'm not gonna say it. I'm gonna actually plug this in and see how it goes. But there seems to be perhaps I'm just visualizing this wrong, you guys, but let's go with it. Let's just go with what's there. I'll go with the notes, but I want to make sure you feel okay about it. Okay, we've seen this. We just saw this elsewhere. And I think the way you want to look at it is only a portion of it, only the portion of the B field that's going parallel to the circle. See, there's a perpendicular portion of it, and when you do the cross product, it's going to be yanking this thing outward, but it's not really torquing it. However, if you go horizontal with it, in other words, the sine of theta is this. The horizontal component would be this one right here, and that would be right here. And if you got I doing this, and you got B doing this, I cross B, bam, into the board. B is doing this. When you get up here, I's doing that. I cross B comes out. So here's I. Here's some sort of B. I'll call it B sub X. Here's I. Here's B sub X. Here's B sub X. Here's I. QV cross B, right? It's like that QV cross B business. Here's I, here's B, here's QV cross B. Roll the fingers of the right hand, bam, into the board. QV cross B into the board. QV cross B out of the board. Yeah, it's gonna rotate this thing. It's legitimate. For some reason, having a little bit of an issue with the drawing there. But all's well that ends well. What is that? IAN is B. Here's mu. Forgive me. Right. Actually, no, that is correct. Actually, let me see how I write that. Yeah, it should be written like this. I wrote it a little differently. But this is the case. Equals. You put in all the numbers that they gave you. You know, what is, you know, for some reason here, where's the, it'd be nice if we knew where the B was. You got the B here. There's something else here, guys, but oh yeah, they had when you actually multiplied it out. So you got 1.21 times 0.2 times the sine of 60 degrees. Plug in all the numbers, guys. I use mu as was. Torque was 0.209 newtons times meters. So it's that. Excellent the way it works. We said it would rotate as it did. You know, the mu that you'd have and the B vector would tell you a lot of stuff. They make it into a vector quantity when they're doing some of this stuff, you guys. If you're rotating this, you're bringing this stuff out. And how the rotation changes. They don't go into that too much. I think it could be a little more of a problem for people than it would be helpful. But I think they go more along the lines of, if you're going to do something like that, you know, mu cross B, it come like out at us like this, and that's indicative of this thing rotating that way. The vector coming out this way means the rotation took place that way. So mu cross B is what mu vector cross B vector for the moment of inertia. Forgive me, for the magnetic moment. So, you know, if you use the magnetic moment that way, a lot of times they're not going to ask you to go there, but if they do, we can do it. So that's some of what we want to talk about regarding this stuff, you guys. Let's do another one. Eventually I think I'm going to, you know, cut this out a little bit and then come back and do some more at a different time. But let's look at Let's look at 55 and we can take it from there. For problem number 55, two long parallel wires separated by 2.50 centimeters carry currents in opposite directions. The current in one wire is 1.25 amps and the current in the other is 3.50 amps. A, find the magnitude of the force per unit length that one wire exerts on the other. B, is the force attractive or repulsive? Let's do 55, and then like I said, we'll stop for a little bit and I'll come right back and we'll do some of the other ones as well. All right, so All right, guys, shouldn't be too bad. So they got the setup. You heard what I said. For 55, how do they want to do that? Could do a whole bunch of things, guys, but we're talking about wires and how they're acting. I didn't in my notes. I just did the mathematics independent of drawing a figure. Let's draw a little bit of a figure. I think it might be not a bad idea for us. They're talking about two long wires parallel to one another. We remember a lot of stuff. We remember that in the back of our mind. This is kind of, in many regards, it's kind of the grandfather of everything that we're doing, or a lot of what we're doing. From here, we can derive a lot of the stuff that we've said. If we're talking about this, from here, you can jump to here. And we can play a lot of games here, guys. We can get rid of the vector notation if we're aware in what direction things are proceeding. And if there's a lot of symmetry and a lot of easy looks we can make, we can kind of get away from the vector notation a little bit. It's always got to be there, though. I mean, these are vector quantities. That's not to be underemphasized. Two long parallel wires separated by 2.5 centimeters. 2.5 centimeters, huh? 2.5 centimeters, let's just cut to the chase, is 2.5 centimeters is 0.025 meters. So we got that. Two long parallel wires separated by 2.5 centimeters, which is 0.025 meters, carry currents in opposite directions. They carry currents in opposite directions. So, tell you what, this guy carries it in this direction. This guy carries it in that direction. Good enough. The current in one wire is 1.25 amps, and the current in the other is 3.50 amps. This one right here, .50 amps, 1.25 amps. Two long parallel wires separated by 2.50 centimeters carry currents in opposite directions. The current in one wire is 1.25 amps, and the current in the other is 3.50 amps. A, find the magnitude of the force per unit length that one wire exerts on the other. B, is the force attractive or repulsive? Okay, a lot of ways to go. Or at least you can give a couple, not about a lot of ways to go, but there's a number of ways to look at a lot of this stuff, guys. You know that. You know this is true. So we got this going on, guys. What happens is, with any current, put your thumb in the direction of the current. Put your thumb in the direction of the current, and your fingers, right hand, put your thumb in the direction of the current, and the fingers of your right hand, the way they roll, will tell you how the B field works. So as your fingers roll here, the B field associated with this guy comes out of the board. If you go here, thumb in this direction, roll the fingers this way, B field comes out of the board as well. So in both cases, the B field comes out of the board. There's two different B fields here. Doesn't matter who you call what. I tell you what, let's look at it. Let's say one thing. Thumb going in this direction, fingers roll this way, it rolls around. Well, the circles are a whole bunch of circles going on into infinity. Circles that get infinitely big in terms of radius. The circle pops out of the board, bam, perpendicular to this guy when it comes that way. Roll, Bam, they come out over on this side. The B field due to this guy, the B field due to this current pops out of the board right here. Pops out of the board, huh? If it pops out of the board and this has I current, what's I cross B? Let me see, put my hand that way. I cross B, so we will go, so I cross B, the B comes out, go this way and roll toward the B. Bam, there's a force going, the force goes that way. Here, right hand rule, bam, it pops out that way as well. I cross B popping out goes that way as well. This is repulsive. It's a repulsive force. Yeah, but there are two different numbers here. Two different magnitudes of current. Is that going to matter? No. This guy creates a real big B field, much bigger than he creates, but this real big B field is only being affected by a small current. Real big B field, small current. Here, so this guy does a real big B field coming right out at us. Bam, comes out at us. So, and we look at it. Here's I. Roll the fingers of the right. Put your thumb in the direction of current. Roll the fingers of the right hand. Thumb in the direction of the current. Roll the fingers of the right hand. The B field circles, and when it circles, bam, it comes out of the board right here. The B field's coming out right here. What's IL cross B? Bam, IL cross B goes that way. This guy, circle, bam, it pops out of the board, popping out of the board. I cross B, thumb goes, I cross B goes that way. So force this way, force that way. Big magnetic field generated by big current, but not a big current right here. So I cross B is a particular force. Fine. Here, this guy, the small current, generates a small magnetic field. Yeah, but there's a big current. They're exactly the same, and they're repulsive. So it's a repulsive force, as we said. And the way it plays, it play a whole bunch of ways here, guys. But at the end of the day, we think it's a 9. I just drew it that way, and of course I put it away. Let me use my eraser then. Here's the B field coming out. That's a 90-degree angle. The sine of 90 degrees is 1, so that's not going to be an issue. So what you got is, I use small l. I could have just easily used big L per unit length. So we'll call this guy, it doesn't really matter. It's kind of the weird thing. You can call this guy I1. And you can call this guy I2. We can use his magnetic field to work on that current, or we can use the magnetic field from that current to work on this current. So in other words, the magnetic field from this I2 can be used to work on this current, or the magnetic field of this I1 can be used to work on this current. It's going to be the same answer. So that is associated with the sine of, we do this, the sine of theta, it's a sine of 90 degrees. It's ILB. I ended up using a small l, guys, so let me try kind of be consistent with my notes so it doesn't scare you as much. ILB right here. Right, that's I1LB is associated. So this is the force. Right, that's correct. That's the force. Yeah, it's sure on him, on this guy. It's I1LB. What's B? Oh, B comes from this one, from the I2. And what is that? Well, that is, from Ampere's law, mu0 I2 over 2 pi r, or 2 pi d in this case, the distance between them. The bigger the distance between them, it's a bigger circle. Yeah, it is a bigger circle, but there's less B field. But the B field is finding itself in many places, but there's less of it. It's essentially, you know, mu 0 I is going to equal the B field times 2 pi r, Ampere's law. Divide by 2 pi r on each side. The r in this case we ended up calling d. That's all it is. So d is the distance between the two. That's the radius, actually, right? Because it's here, and in a radial way, it's radiating out of here. Well, I want the radius to be right here. That's the radius, that's the distance. That's what they want. So this is this. That's good. If it's as simple as that, and it really is, plug in B, plug in B into here. Here's where the B is. The B is here. F equals, yeah, looks good to me. I1 LB. L is the length of the wire. L is the length of the long wire this way. And that's the same length L here. Well, let's not, yeah, we can go there. You could say it for either one because it's not gonna, doesn't really affect much. There's always a little bit of an argument you can make on a lot of this stuff, guys. As you've seen me do already. I mean, I guess you gotta choose your battles. Use what's gonna work for you guys. Plug in B, plug in this value of B right into there, and you got what you need. We already said they were repulsive. We already discovered that. Mu 0 I, that's the B now, the B on the bottom over there in green. B equals mu 0 I2 over 2 pi d times I1L, yeah, times I1L. It's going to be mu 0 I1 I2 L over 2 pi d. There you go. So if we want to know the force per unit length, divide by L on each side, and that L's gone. Here's your answer. It doesn't matter which one you're talking about receiving the force. If you didn't want to go with this guy, and you said, look, no, wait a minute, I want to find the B for the other guy. It's a different B, actually, to be honest. It is a different B. If you wanted to go this way, I2, LB, and this we'll call B, I don't know what good thing to put here. B sub 1 maybe. It's a different. It's coming from B sub 1. It's a different B. I mean, let's get that straight. I mean, that's what that is. And the B1 though, ladies and gentlemen, is mu 0 I sub 1 over 2 pi d. Different. This is different. Yeah, one's B, one's B, and the other one's B1. One's F. I'm assuming it's the same force. action-reaction for Newton's third law tells me it's going to be the same force, but let's see what happens. Maybe we're missing something. And this is I2 L B1. Put B1 right here. Well, it's I2 L mu 0 I1 over 2 pi d. Mu 0, put B1 in there. Put B1 in there. Mu 0 I1 over 2 pi d times I2 L. Mu 0 I1 I2 L over 2 pi d. Mu 0 I1 I2 L over 2 pi d. It's the same thing. Each wire is experiencing the same force, and each wire is experiencing a repulsive force, as we already said. So there it is. No matter how you go, it's going to get there. You saw me do it. Plug in the values. Mu sub 0, and that's not to be confused with the magnetic moment. The magnetic moment vector. This is different. This is a constant. Not the same thing. Mu sub 0 is 4 pi times 10 to the negative 7. I1, yeah, I lucked out, guys. I actually identified the right ones here. I1 is the smaller one. I2 is the bigger one. I1 is 1.25. I2 is 3.50. 2 pi is 2 pi. And D is 0.025, which is 2.5 times 10 to the negative 2. Doesn't matter luck out or not, man. You call these whatever you want. They're the same. They're both going to occur in a multiplication. Doesn't matter what I call what. Still going to be the same answer. Well, at the end of that song and dance, you guys, we got the answer. .5 times 10. 3.5 times 10 to the negative 5. .5 times 10 to the negative 5 newtons per meter is the force per unit length. So if you're considering a long stretch of wire in both wires over a long period of time, yeah, that's a great amount of force. Over a shorter distance, it's the same unit force per unit length, but just a lot of length means a lot of force, according to what we've said already. And that goes with how the pseudo velocity fits into this when you say L over T. If L is a big number and you've associated that, you've associated that big number with, with the movement of charge per unit time with the current, and it's a big length and it's all there, in a sense, you're almost saying it's going a lot faster. It must be going a lot faster. Or at least it mimics as though it were going a lot faster. So, there's a lot to be said there. So there'd be more force associated with it. The force per unit length, yeah, more force associated with it, but there's more length as well for that to be the case. So the force per unit length is identical, whether we're talking about short distances, short length of wire compared to another short length of wire, or long length of wire and long length of wire. Okay? All right, guys. When we get back together, we will go beyond problem 55 and go and start with problem number 58. All right. Thank you. Very short. I mean, we'll have this put together. You'll see directly the start of 58 real soon, as far as how the film is constructed. All right, thank you very much. All right, everyone, welcome back again. Let's talk about problem number 58, and we'll take it from there. There are a few things you're going to see. I worked on this essentially same video that has all these elements united when we talked about the ellipse and its area and things of that nature. So you'll see that, or you've already seen it by now as you're watching this. So it's what it is. Let's go to 58 and let's continue on our process here, guys. Problem number 58 in the Serway book, topic 19. In the figure that I've drawn right there, guys, the current in the long straight wire is I sub 1 is 5 amps. And the wire lies in the plane of the rectangular, let me say this again. The current in the long straight wire is I1 equals 5 amps. And the wire lies in the plane of the rectangular loop, which carries 10 amps. The dimensions shown are, C equals 0.1 meters, A equals 0.15 meters, L equals 0.45 meters. Find the magnitude and direction of the net force exerted by the magnetic field due to the straight wire on the loop. So I2 had 10 amps associated with it. So we've got this. It should go pretty smooth, guys. There's a lot going on here. What you got to kind of watch out for is, there's going to be a current this way. The current's going to come right around back this way and then go that way. So what's going on here? Well, right hand rule here, thumb goes in the direction of the current, the fingers curl, bam, hit this thing right here, the B goes into the board. IL cross B, there's a force going that way. This guy, again, you curl, fingers go right into the board. B goes right into the board, so you got, as we said, we got right hand rule here. B went into the board. I2 cross B, pulling that way. Over here, B into the board again. IL cross B, it goes the other direction, so there's a tug of war. There's going to be less B field the further away you are from the wire. So this force this way won't be as strong as that force that way. So it's a bit of a tug of war. I think we're in pretty good shape. I mean, we can it's going to be a tug of war. The net force is going to be toward, it's going to be an attractive force. This right here is the B goes in here. Bam, right hand rule. B goes in here, do the cross product. The B goes toward the wire. Here, the B goes in there, do the cross product. The force goes away from the wire. Ain't as much B field here. There ain't as much B field here, guys, so it's not going to be the same amount of force. The tug of war is going to be won by an attractive force, a net attractive force going toward the wire with I sub 1 going through it. So, okay, so we do a lot of stuff here, guys. Forces associated with upper and lower parts of the rectangle are equal and go in opposite directions. They cancel. That's something I needed to mention. If you got the B field here, B field like this, and it's going into the board, guys. Again, so it's going into the board here from this guy, and it's going into the board here from this guy, but it's also going into the board here, and it's also going into the board here. Well, let's see here. Going into the board, you got the I here, you got the B field doing this, going into the board, the current this way, go IL cross B, bam, upward. Over here, go IL cross B, downward. There's perfect symmetry here in the lengths, and it's a very long wire. Perfect symmetry in the lengths here, and the current's the same. This guy goes down, this guy goes up. one's pulling up, one's pulling down. The net result is there's no movement in the vertical direction, neither up nor down, because this force and the upward force and the downward force are equal and opposite, so nothing happens. Here's where the tug of war takes place once again. And close to the wire implies attraction. Far away implies repulsion. So there was an attractive force here, as we did the song and dance, and there's a repulsive force here, and, that's fine. So when you do this, you set up the mathematics the way we've done in the past, and that's basically this. The net force Well, look, D2 is a bigger distance. That's the bigger distance. We're thinking it's going to be won by the attractive force there. It will be. If D is big, this whole answer is small. If D is small, this whole answer is big. Yeah, it looks pretty consistent. There's a lot of ways you can do a setup on this, guys. Mu 0 I1, I2, L over 2 pi, 1 over D1 minus 1 over D2. True. The close by one is C distance away, and the far away one is C plus A distance away. So what we're talking about is so we got C right here, and the other one is the quantity C plus A. Well, again, the rest is math. The rest is math, guys. We get it to there, we're good. Plug in all the appropriate values. Mu zero is 4 pi times 10 to the negative 7. I1 is 5. I2 is 10. The length of the rectangle is 0.45 meters. 2 pi is 2 pi. This is 1 over 0.1. They told us C was 0.1. And the other one is 1 over the sum of 0.1 and 0.15, which is 0.25. So it's 1 over 0.1 minus 1 over 0.25. When we do this whole thing, F is equal to 2.7 times 10 to the negative 5 newtons to the left. And we talked about that. I mean, we were trying to get some of the formality of it discussed before we actually grinded out the numbers, guys. But there it is. That's 58. $59. A long solenoid has 1.00 times 10 to the 3 turns. A long solenoid has 1,000 turns uniformly distributed over a length of 0.4 meters. So a long solenoid that has 1,000 turns uniformly distributed over a length of 0.4 meters produces a magnetic field of magnitude 1 times 10 to the negative 4 Tesla at its center. What current is required in the windings for that to occur? We're going to use the formula that we know for that they've already derived for that. We got it in our book, and we know it's going to work. So let's see here. It should be pretty straightforward, guys, based on the stuff we've said. So for 59, they said what they said. It's not too bad. There's pretty easy move to make. I mean, they're saying for a solenoid, after they do the derivation of it, as the Serway book does for us, and as other books do for us, we know that the B field, here's a constant for you. The B field is directly proportional to the amount of windings that you have and directly proportional to the current. Makes sense to me. If there's a lot of windings, there's more chance for a B field. The more windings, triple the windings, triple the B field, all other things being the same. Triple the current, all other things being the same, means triple the B field as well. So if they're directly, now it's not quite as easy to look at that way, but there's a derivation of it, but they come up with a conclusion that's very believable. Now, this is windings per unit area. Windings per unit length. So this is the number, the flat out number of windings divided by the length under consideration. So you've got to get that under control if you're going to do this. Well, why don't we just plug in everything as it is and figure out what we're talking about. We got mu 0 n over L, that's small, the capital N over L, that's small n. And you got this. Let's multiply, let's solve for I. Let's solve for I. You multiply by L on each side. Multiply by L on each side and divide by mu 0 n. That's it. You're done. Based on the formula, believing the equation that's given to us, believing the equation that we know, that's it. You're in a situation where you're calling B. Make sure the units are lined up. 1 times 10 to the negative 4 Tesla. The length under consideration is 4.00 meters, just 0.4 meters is fine. Mu 0 is 4 pi times 10 to the negative 7. And there's 1,000 windings. 1,000 windings over that place. And there you are. The end of the story on that one, guys. Or is it? Yeah, they give a different look at it. I don't think they were saying, for some reason there's two answers here. They probably wanted it to not have too much of a decimal look to it. That's fine. This is not going to be an issue. This is good. If you go and make it 1,000 times bigger, the unit's got to be 1,000 times smaller. This would make it 31.8 milliamps if you play the game on that. So yeah, that's fine. Perhaps the key had gone in that direction, so let's go there too. So that's 59. 60. 60. A certain superconducting magnet in the form of a solenoid of length 0.50 meters can generate a magnetic field of 9 teslas in its core when its coils carry a current of 75 amps. The windings made of niobium titanium alloy must be cooled to 4.2 Kelvin. Wow, we're talking about superconductivity here, guys. Find the number of turns in the solenoid, or at least some manifestation of it. Find the number of turns in the solenoid that would make this thing work. So they're making some statements here, and they're not, maybe they told you what the alloy must be, but that's not the big thing here under consideration. They're saying, okay, what's going on here? How are you going to talk about this? Let's indeed do so. Let's talk about number 60. let's see. I mean, you're playing very much the same game that we just played. So let's keep with it. For the solenoid. Okay. The small n is turns per unit length. This is absolute number of turns over a particular length. Okay. Pretty fascinating in its own regard. We got, again, we're not doing anything new here, guys. You've seen this. You just saw this. What do we got here? Well, we got a lot of stuff up here. Let's multiply by L and divide by mu 0. And then we got N is going to be forgive me, multiply by L and divide by mu 0I, and you get what N is. That's it. They are telling us it's a pretty big feat. I mean, this is how it's going to go. You plug in the values and go for it. B is 9 Tesla. A is 0.5 meters. Mu 0 is 4 pi times 10 to the negative 7. And I is 75 amps. For that to take place over half a meter, just in that half meter, you guys, 47,746.48 turns. Just in that half meter. Just in that half meter to have that thing happen, to have all of that happen, you guys. Let me just kind of look at it one more time really quickly if I could. Right, yeah, it's fine. I mean, that's a lot. In a half meter, that many turns? We said that's roughly equal to 47,746 turns. And there you go. It's a lot. Well, there's a lot being done there. I mean, that's for sure. 74. A straight wire of mass 10 grams and length 5 centimeters is suspended from 2 identical springs that in turn form a closed circuit. The springs stretch a distance of 0.5 centimeters under the weight of the wire. The circuit has a total resistance of 12 ohms. When a magnetic field directed out of the page, indicated by the dots in the figure, is turned on, the springs are observed to stretch an additional 0.20 centimeters. They're observed to stretch an additional 0.30 centimeters. What is the strength of the magnetic field for this to happen? The upper portion of the circuit is fixed. Okay, kind of a neat setup here. There's already a stretch that takes place before you turn on anything. Before there's any other influence other than gravity, there's a stretch that takes place. The stretch takes place because of gravity. There's a stretch of the springs stretch a distance of 0.5 centimeters under the weight of the wire. Once they stretch, they stretch. They've stretched there, and that's their equilibrium orientation at that point. Now there's an additional stretch, independent. We've already accounted for gravity. I mean, we can account for it again, but it's already accounted for, and so you'll see what I'm going to do, how we actually do the problem. What kind of a B field is going to do this? Well, let's look at this thing. Let's try to look at how the whole construction of this takes place, and I think we're going to be in pretty good shape if we do so. Okay, so let's give it a look. Minus plus, we're saying the current is going to go initially out to the left. This is the total resistance that is present. And again, the way they wrote this could be a little confusing unless I write it the way they wrote it. So the way I wrote it could be confusing, actually. This is the resistor. That's the resistor. It's not a spring. The spring's going to show up in a little bit, and they're not going to be highlighted like this. There's a stretch and the whole thing. We'll figure that out. We'll figure all this out. And this is definitely not the way I wanted to draw this thing, but let me give it a little more symmetry. Let me make it the symmetry of what they got, guys. And forgive me, guys. I thought I had a little more room than I actually did. Not that it's a big deal, but just in case. All right, let's try to do this again. This is a resistor. Okay. Springs. Here's spring. You've got the B field coming out, so different books write different things, I guess. They almost always write dots. Sometimes they circle the dot, sometimes they don't, from what I've seen. For better or worse, I'm circling them, but B field's coming out at you. The current goes this way. Current goes this way, this way, this way, and back to here. So how we're pointing this stuff, right? I mean, it's doing this, it's doing that. All right, guys. They're saying various things here. So we're gonna look, well, before anything crazy happens, we know that this thing's stretched. The thing's got a length of 5 centimeters. The straight wire has a length of 5 centimeters and 2 identical springs on it. In turn, form a closed circuit. The springs stretch from 5 centimeters to 0.5. They were originally at 0.5 centimeter length, and they were originally 5 centimeters in length, and they stretch 0.5 centimeters under the weight of the wire. Let's figure out what the spring constant is for the two springs together. The springs are on each side of each other, so they form one, they act like they're one spring. Let's see what that one spring is. And we're doing we're going to do a K, a constant, spring constant for the two springs together. We know before you turn on anything here, guys, before there's any kind of B field that's going to influence the whole situation, we know there's a force mg associated with the wires wanting to stretch. And what happened is a straight wire of 10 grams and length 5 centimeters is suspended from two identical springs that in turn form the closed circuit and the springs stretch. So this guy right here on the bottom, I'm kind of apprehensive to do this. I mean, you put this guy right here on the bottom, that guy got attached and stretched this thing down before any B field was attached. Well, this guy's got weight. The weight of this guy is its mass times G. That is balanced by the net spring constant of these two springs put together. These two springs acting together form one big spring. These two springs acting together form one big spring. Their spring constant is that. F equals F Kx equals mg. What was the mass? It was a 10 gram mass. Let's stay with the MKS system of units. A 10 gram mass is 0.01 kilograms. 9.81 or 9.8 meters per second divided by the amount of stretch. It stretched 5 centimeters. It stretched 0.5 centimeters. That's 0.005 meters. You grind out the math, you guys, and you got the spring constant is 19.6 newtons per meter. The net spring constant. The net spring constant. Well, okay, so far so good. They are telling us, they wrote it already, that's a 24 volt battery and a 12 ohm resistance in total. So 12 ohm resistance in total, 24 volt battery. V equals IR. Yeah, V equals IR implies V equals IR implies I equals V over R. True. V is 24 volts. The total resistance, they describe the total resistance of the circuit as one resistor put in one place, and everywhere else it's not going to be an issue. But it's kind of in aggregate, it comes out to that for our purposes. So they're saying that's 12 ohms. Two amps is what's going through this thing. Okay. If 2 amps is going through this thing, we got a spring constant and everything else, we got to talk. Well, first of all, I don't know, the way they, there's a lot going on actually. For our purposes, they're saying you're not, there's a lot of ways you can talk about this, but here's how we're going to talk about it. Even if the B field was immersed, even if this whole circuit was immersed in the B field entirely, we said up here, somehow, some way, it's fixed. It ain't moving anywhere. Any B field coming out, when you do the cross product, if you go IL cross B, so I's here, IL this way, B comes out, right hand rule, roll the fingers of your right hand, your thumb points that way, there's going to be a force that way. Here, IL this way, B here, your thumb goes this way. There's a force this way. It's the same current now, right? It's 2 amps, same current. It's the same B field. We didn't get it from another wire. We got it from somewhere, and the B field is uniform. What happens is, IL, B goes out, IL cross B, right hand, bam, your thumb points that way, to the left. IL cross B, your thumb points to the left. IL cross B, your thumb points to the right. They balance out. They cancel out. No net force that way. Here, this thing's fastened, so it doesn't matter. I mean, it's doing this. There's a B field out this way. It would tend to want to go up, but it's already fastened, so it's not going to move anywhere from here. Only this guy's going to move. How's he going to move? You got the B field coming out, IL that way, IL going this way, B field coming out, IL cross right here. IL, here's B, IL cross B, bam, bam, goes down. It's going to go down. So that's it. I mean, that's how it's going to work out, you guys. So when you do that, that makes sense. We know it's going down. We know there's still a spring. We know it already kind of fell down, so I don't, we can argue a whole bunch. At least we know what the spring constant is. We now know it's at equilibrium. So we ain't sweating that too much. We know it's at equilibrium, as is. Now where's it going to stretch? It's at equilibrium before you turn on the B field. What's going to happen? These are all 90-degree angles. You saw me doing those cross products. Everybody was hitting. The B field and the IL were hitting one another everywhere at 90-degree angles. There's a lot going on here, guys. In terms of magnitude, let's get the magnitude. As long as we know the direction, the magnitude's the main thing. As long as we know the direction, if we can kind of talk our way through the direction, theta equals 90 degrees. Yeah, that's this. And we also know that force is equal to the stretch, the new stretch that took place. And these forces are equal to one another. What does that mean? Well, if the two forces are equal to one another, Set them equal to one another. If F equals F, ILB equals K delta X. B equals K delta X. B equals K delta X over IL. Sounds good to me. K we said was 19.6 newtons per meter. Delta X was the fall down. It fell another 0.3. It got stretched from where it was. It initially got stretched 0.5 centimeters. And then, okay, we don't care. And then it stopped. It was equilibrium at that point. There was no B field in play. Once the B field was put into this situation, it stretched another 0.3 centimeters. So 0.3 centimeters is 0.003 meters. I is 2 amps. L is 0.05. Gave it to us. Let's stay with this for now. Perhaps this is cause for further discussion if we get a chance to talk in person regarding some of this stuff. All right, guys, it's looking pretty good. We have what we have. I mean, that tells us a bit about topic 19, chapter 19. I call it chapter 19, but it's really topic 19, the way they want to call it. So chapter 19 or topic 19, however we want to call it. There's a whole bunch of other problems that are in here, and or at least a good number of other problems that are in here that I have for you. They will all scroll at the end of this discussion as has been going on, at least in some of the videos that we've been doing, okay? Some of the film that we've been doing. All right, thank you all very much. Take care.